Welcome back to Talk Tensors. You know, we love to break down the most interesting new machine learning research.
Yes.
And today we're going to take a look at a paper that
yeah, this is a good one.
it tackles a problem that sounds like something out of a movie.
Absolutely.
Like imagine trying to find like a
Yeah.
gas leak
Right.
in a huge factory.
Yeah.
Or, tracking pollution as it spreads to like a river with crazy currents, something like that.
Yeah, and this paper addresses those types of problems.
Exactly.
Um,
The title of the paper is,
it's a mouthful.
it is.
Attention-driven hierarchical reinforcement learning with particle filtering for source localization in dynamic fields.
I know it's a lot,
Yeah.
but trust me.
It's a mouthful.
We're gonna make it make sense.
We'll break it down. Yeah.
So what's really interesting here is this paper is tackling this very specific problem.
Yes.
Called
It's called inverse source localization and characterization, or ISLC.
or ISLC for short.
Yeah, it's like a high-stakes hide-and-seek game,
Okay.
but with, some serious consequences if you can't find what you're looking for.
Right, because we're not just talking about, losing your keys here.
Exactly.
We're talking about,
Yes.
safety
Yes.
for the environment.
Right. And the paper outlines some really unique challenges for ISLC.
Okay.
You're often dealing with limited information, so you can't see everything at once.
Right.
And the environment itself is always changing, things like wind currents, even the source itself moving.
Oh, so it's kind of like trying to find a needle in a haystack.
Yeah,
But the haystack's on fire and the needle keeps moving.
that's a good one.
All right.
Yeah. And to add on top of that, the AI needs to be able to handle situations it's never seen before.
Oh, wow.
Yeah, not just the ones it was trained on.
Okay, so it can't just be trained, in a very limited way.
Exactly. And the authors call this out-of-distribution generalization,
Okay.
which is a big hurdle in this type of research.
Wow.
Yeah, think about it. An AI that's trained to find gas leaks in a lab
Right.
needs to be able to perform just as well in a real-world factory.
Right, where things are much different.
Very different.
Okay, so we've established this is a very tough problem.
Yes.
How have people traditionally tried to solve this?
So there are a few approaches,
Right.
each with their own strengths and weaknesses.
Okay.
Some methods use complex mathematical models like Bayesian inference, which can be very computationally expensive.
Okay.
Others are inspired by biology, like plume tracing algorithms.
Okay.
But these often struggle in complex dynamic environments. And of course, we've seen the rise of deep reinforcement learning, or
Yeah.
DRL.
DRL, like the rock star
Yeah.
of the AI world.
They're making waves.
It's like all those AI programs that can beat
Yeah. Beat humans at games.
champions at these games.
Yeah.
But you're saying it doesn't really fit this problem.
That's right. DRL usually needs clear rewards to learn effectively.
Okay.
So imagine you're training a dog to find a lost toy by giving it a treat every time it gets close.
Right.
But in ISLC, those rewards are really sparse.
Okay.
It's like trying to train that same dog, but you only give it a treat once a week.
Yeah, I don't think that dog's going to learn very well.
It'll probably lose interest pretty quickly.
Yeah,
Exactly.
So that's a problem.
Yeah.
So how does this new paper approach things?
They came up with a very clever solution.
Okay.
A 2-layer hierarchical framework that combines the best of both worlds.
Okay.
Bayesian inference and reinforcement learning.
Interesting. So it kind of takes the strengths.
Yeah, like a dynamic duo,
Okay. I like it.
each playing its own role.
Okay, so let's break down this dynamic duo.
Let's do it.
What's the first layer all about?
So the first layer is called the inference layer,
Okay.
and it's all about figuring out where the source is most likely to be, even with that limited information we talked about.
Okay.
And they achieve this using something called an attention-enhanced particle filter. Yeah, so you can think of a particle filter as a way for the AI to make a bunch of guesses about where the source might be, and then it refines those guesses.
Okay, so kind of like a bunch of detectives all working together,
Yes.
trying to figure out where this thing is.
Yeah, each with their own little theory. And
I
they're
see.
constantly sharing clues and updating their theories based on new evidence.
I like it.
Yeah. And the attention part of that is what makes this particle filter special. It's like giving each of those detectives a superpower, the ability to focus on the most relevant information.
So they can cut through the noise.
Exactly. Even in a chaotic environment, they can zero in on those clues that really matter.
That makes sense, especially in these, crazy search scenarios.
Yeah.
What about the second layer of this dynamic duo?
So the second layer is called the execution layer.
Okay.
And that's all about actually navigating the field and getting to the source.
Okay.
And the authors actually give us two approaches here, ATTPFP and ATTPFRL.
Two approaches.
Yeah. So ATTPFP, that stands for Attention Particle Filtering Planning.
Okay.
And ATTPFRL stands for Attention Particle Filtering Reinforcement Learning.
Okay. So is it like choosing your mode of transportation?
Yes.
Like taking a train versus driving a car?
That's a good analogy.
Okay.
So ATTPFP is like using a detailed map.
Okay.
It's a systematic planned approach that works well in structured environments.
Hmm.
Imagine searching for a specific book in a well-organized library.
Yeah.
You probably wouldn't just wander around randomly hoping to stumble upon it.
You'd follow a map.
Yeah, you'd use a systematic approach, checking each section and shelf.
Right.
Logically.
So that's ATTPFP.
Exactly.
What about ATTTFRL?
That's more like driving a car.
Okay. Yeah.
You can adjust your route based on traffic and road closures.
Yeah.
So it's more adaptive and better suited for unpredictable, constantly changing environments.
So more like a GPS.
Exactly. It's like having a GPS that updates in real time based on traffic conditions.
Okay, so you can kind of, go around those obstacles.
Find the fastest route.
Yeah.
Yeah,
Pick the right tool for the job.
exactly.
I like it.
Yeah.
But before we get into how these approaches work,
Hmm.
I think it's important to understand how we got here.
Absolutely.
The history
Yeah.
that led to this breakthrough.
To fully appreciate this paper, we need to trace those key ideas that led to it.
Right.
And that takes us on a journey through AI history,
Okay. I love a good history lesson.
starting with Alan Turing.
The legendary code breaker.
Yes, the visionary who laid the groundwork for AI.
The Turing test.
Exactly, the idea that a machine could be considered intelligent if it could carry on a conversation just like a human.
Right.
Yeah. So his ideas back in the 1950s sparked a wave of research into how to create these machines that could learn and solve problems.
Yeah.
And one of the early milestones was the development of the perceptron,
Cool.
essentially the first artificial neural network
Wow.
back in the late 1950s.
So those were like the baby steps
Very beginning.
towards these huge neural networks we have today?
Exactly. And those baby steps led to some major advancements, like the
Right.
development of backpropagation
Back
in
propagation.
the 1980s,
Yeah.
a really clever algorithm
Okay.
that allows for efficient training of multi-layer neural networks.
Wow.
It was a big moment that
Yeah.
paved the way for this deep learning revolution that we're seeing.
Deep learning, that's when AI really went mainstream.
Exactly.
It's everywhere now, from image recognition to language processing.
It's everywhere.
Hard to imagine the world without it now.
It is.
But how did reinforcement learning evolve alongside all this?
So reinforcement learning has its own fascinating history,
Right.
dating back to the 1950s with early work on learning automata.
Okay.
But it really started to gain momentum in the 80s and 90s with the development of key algorithms like Q-learning and temporal difference learning.
Q learning, that rings a bell.
Yeah,
That's behind some of those amazing game-playing AIs.
yes, like AlphaGo.
The one that beat the world champion Go player.
That's right. Q-learning lets an AI learn optimal actions by interacting with an environment.
So they learn by doing.
Exactly, by doing and receiving rewards or penalties.
Right. Kind of like, training a dog with treats.
Exactly like teaching a dog new tricks with treats and scolding.
Right.
But like we discussed with ISLC, those rewards can be few and far between.
And that's where Bayesian inference comes in.
That's where it comes in.
Okay, so let's talk about Bayesian inference.
Let's do it.
What's the history there?
So Bayesian inference goes all the way back to the 18th century
Wow.
with the work of Reverend Thomas Bayes.
Okay.
Yeah, and it's all about updating beliefs based on new evidence.
Okay.
Imagine you have a hypothesis about something.
Right.
Then you gather new data
Uh-huh.
that either supports or contradicts that hypothesis.
Right.
Bayesian inference gives us a framework for adjusting your belief in that hypothesis based on that new evidence.
So it's kind of like constantly refining our understanding of the world.
Exactly, as we gather more
Mhm.
information. And this is especially useful in situations with a lot of uncertainty.
Right, like our gas leak or pollution example.
Exactly, like trying to locate that hidden source in a dynamic field.
Okay.
And what's really amazing about this paper is how it brings together these two seemingly distinct fields,
Yeah.
reinforcement learning through trial and error,
Right.
and Bayesian inference reasoning under uncertainty,
Okay.
to create this really powerful framework for solving these complex search problems.
It's so a really cool combination.
Yeah, it's a testament to the creativity of AI researchers.
Yeah, they're always pushing the boundaries.
Always.
I, for one, am very eager to see how they put this into action and what kind of results they got.
Well, then let's move on to part 2,
Right?
where we'll delve into the technical nuts and bolts of this groundbreaking research.
Okay, let's do it. Welcome back to Talk Tensors. In part 1, we kind of set the stage right. We talked about the challenges of ISLC
Yes, inverse source localization and characterization.
and that clever approach they took in this paper.
It is a clever approach.
So now let's get into the nitty-gritty.
Yeah, let's dive deeper.
How did they actually model these complex dynamic fields?
So one of the key ingredients here is a mathematical equation that you might remember from physics class.
Oh boy.
It's the convection diffusion equation, or CDE for short.
Okay, CDE, got it.
It describes how things spread out over time due to both random motion and bulk flow.
You're going to have to break this down for me,
Okay, sure.
because I think a lot of our listeners might need a little physics refresher.
Yeah, that's fair.
So can you give us a real-world example?
Absolutely. So picture this. You drop a drop of food coloring into a glass of water.
Okay, I'm picturing it.
What happens?
Well, it starts to spread out, right?
Exactly.
It's like a little cloud of color in the water.
Yes, that's a diffusion at work.
Diffusion.
The dye molecules are randomly moving around, spreading from areas of high concentration to low concentration.
Okay, that makes sense.
Now imagine you stir the water with a spoon.
Okay, I'm stirring.
What happens
Well,
next?
now the dye is spreading out faster.
Yeah,
And in a specific direction because of the current from the stirring.
exactly. That's convection.
Convection.
The movement of the dye is now influenced by the bulk motion of the water.
So it's being carried along by the water.
Exactly.
Okay.
The CDE combines both of these processes,
Interesting.
diffusion and convection,
So in this paper, the substance could be anything.
right?
All right.
It could be a gas leak, a pollutant, even heat.
And it's spreading out in this complex field,
Exactly.
influenced by things like wind or water currents.
You got it.
Okay. So the CDE provides a framework for modeling how these fields behave over time.
Exactly. But the authors actually used a simplified version of the CDE called the Gaussian plume model.
Gaussian plume model,
It's specifically designed for modeling things released from a point source.
like a plume of smoke rising from a chimney.
Exactly.
Yeah, I can picture that.
The Gaussian plume model captures how that smoke spreads out, becoming more diffuse as it travels farther from the source.
So it starts out concentrated and then
it disperses.
disperses.
Yeah, and this model is really important in that inference layer, where the attention-enhanced particle filter comes into play.
Right, the tiny detectives.
Yes.
Trying to figure out where the source is.
They are.
So how does the Gaussian plume model help them do that?
Well, it helps them make those educated guesses.
Okay.
So think of each particle as running its own little simulation of the plume,
Okay.
based on the Gaussian plume model,
Uh-huh.
trying to match it up with the real-world data coming from the sensors.
So they're comparing their simulated plumes to the actual sensor readings
Oh, that's right. Okay.
to figure out where the source might be.
So it's kind of like a puzzle.
Yeah, they're trying to fit the pieces together.
Right. They have some pieces from the sensors,
Yeah.
and they're trying to create a picture that matches.
Exactly. And the attention mechanism is like giving them a magnifying glass,
Okay.
allowing them to focus on those most important clues.
Cutting through the clutter.
Yeah. Ignore that irrelevant information. Yeah.
But the real magic happens when we combine this with reinforcement learning.
Yeah. I'm still a little fuzzy on how they merged these two approaches.
Sure. So remember, traditional reinforcement learning relies on clear rewards or punishments.
Right. Like training a dog with treats.
Exactly. But as we discussed, those rewards are scarce in ISLC.
Very scarce.
Right. So that's where Bayesian inference steps in,
Okay.
helping the AI make better decisions even without that constant feedback.
So Bayesian inference is kind of like a guide
Yeah, a guiding hand.
saying, hey, based on what we know, these areas are more likely to contain the source.
That's a good way to put it.
And then reinforcement learning takes over and figures out how to actually explore those areas.
Exactly. So the inference layer uses Bayesian inference to estimate the probability of the source's location.
Okay.
And the execution layer, guided by reinforcement learning, uses that information to decide where to move next.
So it's like a beautiful dance between these two layers.
It is a beautiful dance.
Okay, I'm starting to see why this paper is so exciting.
Yeah, it's a clever approach.
But did it work?
Let's talk about the results.
Yeah. What kind of results did they actually get?
So they ran a bunch of simulations testing their framework in all sorts of scenarios.
Okay, so they really put it through its paces.
They varied things like the size of the field, the complexity of the environment, the type of source, even the noise level of the sensor readings.
So they really tried to make it difficult.
They did.
Okay, how did it hold up?
The results were really impressive.
Okay.
Across almost every scenario, their framework outperformed existing methods.
Wow.
It was faster, more accurate, even in those environments where the conditions were constantly changing.
So it's robust.
It is,
Adaptable.
yes, very adaptable.
But what about those out-of-distribution situations?
Ah, yes, the scenarios it hadn't specifically been trained for.
Right, because that was one of the big challenges.
A major challenge.
So how did it do?
It showed remarkable generalization capabilities,
Meaning?
meaning it could adapt to new situations it hadn't seen before.
That's incredible.
It means this technology could potentially be applied to those real-world problems where you can't anticipate every variable.
Wow, this is really exciting stuff.
It is.
But before we get too carried away, let's shift gears and move on to our novel notions segment.
I was hoping you'd say that.
It's time to unleash our imaginations.
Time to speculate.
Welcome back to Talk Tensors. We've spent the last two parts, diving into this paper.
Yeah, it's a fascinating one.
Really pushing the boundaries of AI,
Absolutely.
using this clever combination of Bayesian inference and reinforcement learning
It's a powerful combination.
to find these hidden sources.
Right, in complex environments.
But now it's time for my favorite part of the show.
Novel notions.
Novel notions time,
Let's do it.
where we let our imaginations run wild.
Yeah, time to speculate.
So we've talked about, searching for gas leaks.
Yeah, and tracking pollutants.
But what other problems could we solve with this framework?
So one thought that comes to mind is drug discovery.
Drug discovery. Wow, it's a big jump from, finding physical sources.
It is, but think of it this way.
Okay.
Imagine that huge universe of potential drug molecules as a massive complex field.
Okay.
Each molecule is like a point in that field.
Okay.
And its properties, its effectiveness, its side effects, its stability, all that stuff determines its location.
So instead of searching for a physical source, we're searching for a molecule
Exactly.
with the right properties to treat a specific disease.
You got it.
Okay, I see where you're going with that.
Yeah, and just like those problems we've been discussing.
Right.
This surf space is huge and complex.
Incredibly complex.
Yeah, traditional methods are slow and expensive.
Yeah, a lot of trial and error.
A lot of trial and error.
So how could this hierarchical framework help us find, these miracle cures faster?
So picture using that powerful inference layer with its attention mechanism to efficiently explore this molecular space.
Okay.
It could analyze data from previous drug discovery efforts,
Okay.
identify promising regions, and guide the search towards molecules with a higher chance of success.
So it's like having an army of AI chemists,
Yeah, sifting through mountains of data.
pinpointing the most promising leads.
Exactly.
And then the execution layer could take over.
Right, using reinforcement learning to design and test those new molecules.
Oh, wow. So like an AI-powered laboratory
Exactly.
running countless experiments in the blink of an eye.
At lightning speed.
But wouldn't this need massive amounts of data
It would.
and computing power?
It would require a lot of resources.
Right.
But remember, one of the key things about this framework is its ability to learn with limited information.
Right. It's designed for sparse rewards.
Exactly.
So even with limited data,
it could still make breakthroughs.
wow, that would have taken us, years to figure
Or
out.
possibly decades.
Yeah, it's both exciting and a little bit scary at the same time.
It's definitely a powerful technology.
It is.
But it's important to remember that this is still speculation.
Right, we're in the novel notions segment.
We are.
So we're allowed to dream a little.
There are definitely hurdles to overcome.
But it highlights a broader point.
Which is?
The breakthroughs in AI aren't just about solving one specific problem.
Right.
It's about these new ways of thinking
Exactly. New frameworks.
that we can apply to all sorts of problems.
do a wide range of challenges.
And this hierarchical approach with Bayesian inference and reinforcement learning is a perfect example of that.
It is.
Who knows what other applications we'll find in the future?
The possibilities are endless.
I'm very excited to see where this research leads.
As am I. It's fascinating.
It really opens up a whole new world of possibilities.
It does. It pushes the boundaries of what we thought was possible.
Well said. Well, on that note,
Yeah.
we've reached the end of our deep dive into this paper.
It's been a great discussion.
We covered a lot of ground.
A lot of ground, from the technical details to the broader implications.
And as always, the link to the paper's in the show notes.
Yes, check it out.
If you enjoyed this episode, be sure to subscribe to Talk Tensors for more insightful discussions on machine learning research.
And until next time,
Keep those neurons firing.
and keep exploring.
Goodbye.